Okay, welcome back. I hope you all had a good, nice lunch. It didn't rain, the weather is nice, so I hope you're all relaxed and ready for the final session of the day and also the final session of the PhD school. So for this session, our speaker will be Manfred Scheucher. So Manfred he studied originally at TU Graz, unless I'm mistaken. He did his bachelor's and master's there. Then for his PhD, he went to Berlin, where he studied under Stefan Felsner. Currently, he is also in Berlin. He was employed on his own DFG project. And yes, he will be speaking about something which one could also consider interdisciplinary, which is in particular this intersection between graph drawing and SAT solving, and how to use SAT solvers to make progress on computational geometry and graph drawing questions. So you have the floor, Manfred.
Thank you very much. Okay, so this talk, these two sessions today will be split into 3 parts. In the first, I will give you some basics, and there will be examples all over all 3 parts. In the second part, it will be some smaller applications, and in the last part, I will tell you about the biggest project that I worked on in the last years. It took me almost 9 years to solve it, but it somehow worked out, and so this will be a part on its own, even though it's just one specific application. And throughout the entire session, so there will be like a 90 and a 60-minute slot, I will place examples everywhere. Everything will be interactive. So I have on the URL here, I will put it also on the slides. It will be clickable for those who are watching. So I have examples on Google Colab, which you can download also and run locally on your computer using Jupyter Notebook. There's some short explanation here, so everything is just very easy to click and copy paste if you want to run Jupyter on your local machine. And there will be some exercises. So I will stop in between these 90 minutes, make some breaks so that you can digest and try to actively solve some of the tasks. And please feel free to interrupt and ask at any time. So just stop me, because if I'm too fast, which I usually tend to be, it's very good to slow me down. It's not my goal to speed up, get through all the slides. So if we cannot make it till the end, that's no problem, then maybe I skip something in between. So just feel free to slow me down if I'm too fast. It's important to repeat, and the goal of today is also to teach you something and not to present my work. Yeah. So please just stop. Yeah. Just shout stop. Okay, and I will try to speak slower. Okay. So the first link which I wrote here and also here on the blackboard, this is just on my website. If you have to type it on your mobile phone or whatever device you use, it just points you to this one. I didn't want to write this one here. I could have used some short URL. Essentially, there's also the solution to one of the exercises, but don't get spoiled if you want to seriously work on it. It's just afterwards you can look up the solution. Okay, so what is SAT? Yeah? SAT is just a basic question. You're given some Boolean variables, and there's a formula. And the formula is essentially just a mapping. Every variable is assigned to true or false, and the formula is then fulfilled or not. And the formula might be very complicated. You don't know in the beginning, is there an assignment or not? And the problem is to figure out whether there is an assignment so that it evaluates to true or not. And of course, SAT is NP complete. It was the first NP complete problem with Cook's theorem. There's game over. Yeah? You cannot do it efficiently. But I will tell you a little bit how the solving strategies are. But this will be in a couple of minutes later. So first we will try to get into the formulation, what is the setup. essentially, you can consider SAT solvers as black boxes for now. Just consider the challenge of today to model a specific question. So we don't want to do logic today. Yeah? So the goal is we want to have some graph theory problem or a graph drawing problem or geometric problem. We want to model it with logic, use those black boxes, and the black box should tell us, yes, your question is answered with yes, or no, it's not. And yeah, and we really benefit also from the current solvers. So there's a strong development in the last years. And nowadays you can even verify that the solvers are correct. So it's not that you write your own C++ code and then it returns true, because there might be some bugs or whatever. So of course you can make errors when modeling your question. Yeah? If you put down the rules, your conditions, you might make some mistakes on this level, but provided that the model is exactly what you're looking for, the SAT solvers work correctly, and you can verify, and this is verifiable. And there's even some additional way how you can verify the modeling process, but I'm not going to talk about it. So if you're interested, there can be another lecture about this. So there's really a large community doing model verification where you can formally verify existing proofs. And just as a spoiler, if you want to verify that the square root of 2 is irrational, so there's a very short proof, if you want to write it down with a computer, it takes you some time to do it. Yeah, I mean, I can do it on the black. Most of you have seen this proof, probably all of you. If you want to do it by computer, it takes some time to see what is going on, but it exists. So it's possible not only to solve a problem, but really to verify that the modeling was correct and the solving was correct. And yeah, today the focus will not be on verification and certifying something. So we want to solve questions or learn to solve questions, and we will use Python with the PySAT interface to the solver Kadicar, which is currently, it's not the fastest one. So there is KISSAT, also developed by the same guys from Freiburg, Germany. But Kadicar has a nicer interface. So I will talk about mostly Kadicar because you can address it from PySAT. Essentially, KISSAT is a C implementation and Kadicar is the C++ implementation, and they have similar behavings. You can talk about most of the topics which I start today for more than 15 minutes, much more. So I have to try to sneak around most of the things. Yeah, and also you don't have to use Python, of course. You can use C++ or any language that you want to formalize these models. And again, please interrupt me. I mean, this slide was quite boring. Sorry for that. Let's start into business. So usually we have a formula which has some other operators like A implies B, or you can have in both directions. But the standard is to only look at conjunctive normal form, which means there's only AND, logic AND operators, and logic. There's a mistake here. This should be an OR. Sorry. So this should be opposite. I will correct this. On the first serious slide, there was an error. Okay, this is a logic OR. So we have a lot of this would be easy to solve. Yeah. So if you have an instance like this, it's O of 1. No, I mean it's no, actually it's not O of 1, O of n. But it's you give them a lot of clauses, and each clause consists of logic ORed literals, and each literal is either a variable or a negation of a variable. And here's an example. Here I have the correct one. This is an OR now. And if you see a formula like this, you encode it in Python or even in C++. What you do is usually you make a list of lists. And each list here is a clause. So those are the ors, and the outside list is for the ends. And if you want to solve this instance now with Python, you can install PySat. So you just run pip install this thing. There's also additional packages. You don't have to install all of them. This is just the installation thing from here. If you run it with this CoCarc, now how is it called? Colab, Google Colab, then just install everything of those. It doesn't matter anyhow. The thing is, if you have it installed, you just write down the CNF, start a solver with the CNF, and then just you can enumerate all the solutions. What happens if you run this code is you will see that there are 6 solutions. Notice that there's 3 variables, like 1, 2, and 3. This is x1, x2, x3. So essentially there would be 2 to the 3 equals 8 assignments, and 3 of them are killed from the truth table. So each of those clauses kills 1 line of the truth table. This is essentially how you can think of the trivial way of determining satisfiability, but we will come to more efficient strategies later. For now, it's just important to see how you can put logic problems into the computer. There's a format which is called DMAX standard, and it looks like this. We usually write comments, so you can put as many comments as you wish there as well. But essentially, you have a first line which specifies the number of variables, the number of clauses, and you have also then all the clauses, and each clause is ended by a 0. Essentially, you don't need to have line breaks, I think, but it's good to do so. And why do I mention this DMAX thing? You can create instances inside of Python, C++, whatever. You write it to this CNF form, and then you can just use whatever solver you want. You can use Cadicar, Picosat, Minisat, whatever, and just run it from the command line, have different solvers. You can also try to do it inside of Python to start all these things. But the nice thing, which I usually do, is I use Linux. You can also do it in Mac. Also from Windows, you can use some integrated Linux or whatever to use pipes. Yeah? What I do here, I use a pipe. So there's a lot of more solutions, and there's also some output parameters you can get rid of. Just look at all the programs. They are written by different developers. They don't have standards what the output should be, except for saying S means this line defines whether it's satisfiable or not. This is a standard, and V gives you the assignment for the variables. And as you can guess, this means x1 equals true, x2 equals true, and x3 equals false. So this is how you should read the output of such solvers. And here there would be more output, and I use a grep command. And what does this mean here? I guess most of you are familiar with using bash or command line operators. If you're not familiar, I will just have one short slide to give you some idea what you can do. So with this grep v, if I would omit this symbol here, I would just only show lines which contain a v symbol. But with this symbol in the beginning, I make sure that the v is on the first place, so I don't accidentally grab other output lines. If you're not familiar with pipes, if you have multiple programs and you want one program to take the output of the previous program and so on, and maybe in the end you don't want to print it in your command line but really put it to a file, you can use pipes like this. And then there's redirecting operators like this one, where you really create a new file, or with this symbol you can append it to the end of the file. So it's really nice. It's a nice thing to use command line if you want to solve problems. as an academic. I already explained the V. You can use regular expressions. It's really very comfortable in some places. You can use, I mean, essentially you can also write some Python code to parse all your stuff. But there is some standard commands like set or awk where you can just easily, with very short effort, modify stuff. And of course, there's a lot like sorting the outputs or just unifying if you have duplicates, counting the number of lines, especially if we just grab how many solutions there are, we can see it from the number of lines. Head, tail just gives you the first or the last entries of your solutions or whatever you do, and many more nice commands. As I mentioned in the beginning already, logical formulas might also contain other, if you describe them, you might use other symbols than just or and and. So if you're given something else, you can you can start rewriting. But even if you restrict it to and, ors, and negations, putting it to C and F can be a little bit difficult, because if you just use De Morgan's law and distributive properties, it can go to exponential size. So there is a better strategy. So you can use additional variables and the Zeitin transformation to keep the formula relatively small. So why do I say exponential? If you look, for example, at this rule here, you see that on the left side there was just the A, but on the right side what we do is we have two A's. So if A is a longer formula, it will just duplicate. So the size really blows up by a factor of 2 if A is big. And if you have this recursively, it can really blow up. How does the Zeitin transformation work? If you have P, Q, R, and some S, this can be variables or formulas. It's essentially the here in this example, you can consider it as variables, but essentially this is like a meta example. So it can be a formula with formulas inside. But what you do if if you consider this example with variables, is you introduce new variables for each sub-formula. And you start with the smallest sub-formula, like this negated S is the smallest sub-formula here. On the left side you have this formula here, and the smallest one is, I mean, you wouldn't have to do this negated S if you do it smart, so you could get rid of it. But essentially you have the R here, you don't need to introduce another symbol for this. This is the next smallest thing, and you introduce another variable which indicates whether this is true or false. And then, if you have like a variable, if you have the value of this and you know the value of this, you can combine them and say x3 encodes whether this expression is true or false. And in the end, you introduce a variable which indicates whether the entire thing. So you build it up from scratch, bottom up. And essentially you can even get rid of this last variable, because you have to put it to true anyhow. You want to know if this formula is true or false, but this is for the idea. And also this is from Wikipedia, this example. So I put the link here. You can read in more details how these steps are done. So far I only mentioned you can introduce variables. They don't have meanings. Yeah, if you just say I have now 4 variables like P, Q, R, S. I introduce another 4 variables, so I have 8 variables in total, and I want to make sure that those variables here, they really encode what they should encode. So what I have to do is I have to introduce clauses to make sure that x1 is really the same as the negation of S. How do I do this? I rewrite the left-right arrow to the right arrow and also to the left arrow. So this is just flip. And then this arrow is the same like the left side negated and here also negated. So you have essentially two clauses for these rules, and you continue for every other rule as well. So here again, you have this expression here. You do the same thing with the arrows, and you end up with clauses. And this is possible for all rules in constant size, because what you have here is always an operator on two things. So it will involve at most 3 variables. So it's really a constant size per variable, and you only have a linear number of variables added. This is why Zeitian transformation is really nice. Okay, so this is already the first exercise. If you want to practice a little bit, you can think of how to transform this formula. So everyone roughly has an idea how to do this, or should I resolve it? Should I arms up for resolving it, or just continue? Continue. Okay. Okay, let's now get to some serious thing that we all work with, graphs. If you have a graph, undirected or directed is essentially, it doesn't matter. We will look now for undirected graphs. You have vertices. We have vertices from 1 to n, and you have sum of the edges. And what you want to do if you encode it with SAT is you want to use variables for indicating whether an edge is present or not. So you have essentially n choose 2 variables. If it's a digraph, 2 times, yeah? And those variables indicate whether the edge is here or not. And if you want to attack a problem like Ramsey numbers or whatever graph theoretical question you want to solve, you have to do some constraints. Yeah, if you just have variables, there's nothing to solve. So how would you address Ramsey numbers? Everyone knows what Ramsey numbers are, or should I define it? Okay. So we want to forbid a complete graph in the graph and the complete graph in the complement. And essentially to show that the Ramsey number ARB is equal to some value n, we essentially make some queries. So to show that it's equal to n, we show that it's at least more than n minus 1, but it's not bigger than n. So those are 2 queries which we have to do. So essentially, you can go step by step. You can test: is it at least 1? Is it at least 2? Is it at least 3? And at some point it will stop, and then you know, aha, the last value was the right value. And if you already know the answer, you don't have to do the search by yourself. But essentially, if you address a new problem, you will have to do some steps to make a guess, even if it does not terminate. So if you look at current Ramsey numbers 5566, something like this, which are unanswered, there are some lower bounds, because for Ramsey numbers you just need to find a graph which does not contain complement Ka, and the complement doesn't contain Kb. Then you know, okay, the Ramsey number has to be bigger, but you don't know if it's really equal. Yeah, so you cannot maybe prove. So at some point it might become difficult, but essentially you can get an idea of whether it works or not. So Ramsey is definitely a good example, because there's this saying that if aliens should attack the world and ask humanity to solve R55, we should put all the computers together and try to solve it. But if they want to have the next value, we should put all our energy and try to destroy the aliens, yeah? Because it's impossible. And maybe in 200 years people will think differently, but with nowadays machinery. Okay, for Ramsey, if you want to implement it, you can use PySat. They have a nice interface for variables. So what you essentially do is you say, I have vertices this is from 1 to n, but more specifically from 0 to n minus 1. Yeah? I wrote 1 to n before on the slides, but what Python does with the range, this is a list with values from 0 to n minus 1. Then here I just say I want to have some variables, yeah, at some point. Then I say I have here, I want to have some, for every edge I want to have the variable. And how many edges do I have? I have combinations, vertices, choose 2, which gives you like pairs like 0, 1, 0, 2, 0, 3, 0, 4, 1, 2, 1, 3. So this will give you all the ordered pairs, and for each of them, it will give you a new variable with this command here. So PySat really takes care that those are distinct variables, but you can even write here in the parentheses if you call this function multiple times, you will always get a new variable. If you want to get the same variable, you can also write vpool dot id, and then you can write something like, I don't know, just some identification, edge I, j, or you can even format it as a string. So in Python you can write it like this and make a format string. There's a lot of options. I don't want to put all the options there. Essentially what it does, if you put some argument here, string, tuple, whatever, it will map it. Yeah? So it has an internal dictionary. It will look it up if it had it previously. What I usually do is I declare all the variables in the beginning. So if I, by accident, access something that I didn't allocate, then I notice I made some mistake in the model. So that's why I usually define the variables before. This is like a C programmer. Yeah, it's not really necessary to do it like this, but I have a little bit more control. And sometimes you make a mistake, and then you might swap here. And at some point, it might be that you want to access and you want to know if 7.2 is an edge, but actually you had it 2.7. You wanted to switch it, or stuff like this can happen. And so that's why I usually put the variables on top, and then I start modeling the constraints. And for the constraints, if I want to forbid Ramsey numbers, I go over all possible subsets. So with Python combinations, you can choose all the possible subsets. So maybe I also share the picture if I'm now pointing. Okay, so usually with combinations you get, not usually, always. with combinations you get all the subsets of size A. And what I do is for every pair from this selection, I want that one edge is missing. So in this way I can make sure that in this selection here, in this induced subgraph, it's not a click. Yeah? If I know that one of the edges is missing, it cannot be a click. And the same for the complement. So I want that the complement doesn't contain a KB. So for every B vertices, I want to make sure that there's an edge. This is the entire Ramsey program. And now, let me show it. Because I actually prepared everything nicely, so why should I not show it? Should be there. Does it work for all of you? I guess all of you clicked on it, or not all, but most. Okay, okay, so you see, okay, the installation. This was the previous example. Here's the Ramsey number codes. Exactly what I have on the slide, had on the slides before. If I want to solve Ramsey number 3.3, I can now just say I want to have the instance 5.3.3. I have these parameters n, a, b here. And as a second return value, I also give back the edge values. Not only to know if it's true or false, but I really want to print the graph. So what I do here is for every solution that I find, I want to look up the edges. Yeah? So the SAT solver just gives me the assignment. It gives me x1 was true, x2 was false, whatever. And the question is, what is x1, x2, x3? And for this, I relook up the variables. And this is quite easy, quite nice. With this code, you can immediately see. And what it shows here to the left is the assignment of the variables, and here are the edges. And you can continue then with larger Ramsey numbers, but I think I will continue as I have in the slides. So a general advice, as you saw, I made this function with parameter n, a, b. I would always use parameters flags and not try to change in the code too much, because this is a common source of error. Because if you have multiple places to change the constants and you forget one of them, or you were debugging something and you forget to comment something in again or something, just try to use parameters flags. If you use command line, you can use command line parsing. So Python has really nice arg parsers. C++ has boost. If you never used it, you can have a look. It's really very, very nice to use. Or you can even use graphical interfaces. So if you use Qt or Java or HTML or whatever. Yeah, so this is again the same but different. This is a word I had it at sausage at some point. This is again all the solutions for the Ramsey five vertices, no k-free and no free click, no free anti-click, and as I said, you can read the edges, and if you draw the graph, you can convince yourself that there's really no click, no free click, and no anti-free click. And if you run the next one, so with 6, you will see solutions none, yeah? Which means that the Ramsey number is 6. And I really, let me skip this certification. I really recommend to visualize all the data. Whenever you get something, just double check, because sometimes you might notice that there was some mistake when formulating. And if you visualize it and everything is fine, this is done in a few minutes. But if you spot something, this is worth gold, because you could continue working with errors for days, and at some point you will figure out that there's an error. Or even worse, if you publish results and it was wrong, then it might be too late. So always try to visualize. I used a lot SageMath, because it really has a nice interface for graphs, but you can also use whatever, Network X, Matplotlib, GraphViz, Boost. There's a lot of, I mean, there's also other computer algebra systems like Wolfram. I think Wolfram Alpha can also do it. The reason why I use Sage a lot was because it's Python. Essentially, you have the same code in Python and in Sage, and Sage is essentially just Python-based. Okay, the next exercise is, you should think of, you don't have to implement it, just think, how would you model Sudoku as a CNF, as a SAT instance? So I guess everyone knows what Sudoku is. So the general constraints are written here in text form. You have a table, 9 by 9, which is partitioned into blocks, 3 by 3 blocks. So there's like 1, 2, 3, 4, 5, 6, 7, 8, 9 blocks. And the constraint is every field gets a value such that in every row, in every column, and in every box, every value appears exactly once. That's Sudoku. I guess everyone knows. Yeah.
Just to get started, so you would have a 9 by 9 array that
Exactly.
has an array of length 9 that is kind of an indicator, where you say,
Exactly.
okay, the value in this cell is
Okay.
so 3-dimensional.
Exactly. So what you do is you have, let me write it down, because not everyone can hear you on the stream. So the idea is to use variables. So you use, let me call it R, C. So you use variables for every row, column, and value. So row, column, and value, all of them are in the range from 1 to 9. And you say, this is true if and only if the value, so let's call it table, yeah? If the table at row column equals V. This is the starting. This is how you encode the values. And to be a little bit fair, encoding blocks is a little bit tricky, yeah, because you have to think how do you make the blocks. But rows and columns are pretty easy. So what you do is for the rows, you just make essentially a for loop. You say for every row, you insert a clause. Let me think. For every row. Now, and actually, okay, we want to see in every row, we want to see every value. And if we see every value at least once, we see every value at most once as well, yeah? Because this is a finite thing. So we say for every row and for every value, we add, we append a constraint, and we say we want to see that RCV is true. So whenever we write CNFs in Python, to say it should be true is just to write down the symbol. If you want to have it negated, you make a minus. Because what PySart does, it just uses integers to represent variables, and positive integers for variables and negative for negated. Yeah, and this is also a reason why PySart starts indicating with 1, yeah, because the negation of 0 doesn't make sense. So, in case you wonder, this might also be a common mistake. Okay, so we want to have this for every column. So here, for every row and for every value, we make one additional clause, and the clause contains now 9 values. So we say, for example, if we pick the first row and we pick the value 1, we say that in this column or in that column or in that column or in that column, it has to be the value 1. And we do this for every row, for every value, so we have a quadratic amount of constraints here. And the same thing is for columns. We do the same for columns here. I have actually prepared the code to show you. If you don't want to see the code, you can close your eyes for a moment, because I also prepared the... Now you can keep your eyes open for the moment. It takes some seconds. So okay, here in the same spreadsheet that I shared to you, there's the assignment, and I also put a function with chunked where you can group the grid into chunks. Yeah. So if you use the list from 1 up to 9. And you say, I want to have the chunks of size 3. What it does, it gives you like 1, 2, 3, 4, 5, 6. And if you look at the Cartesian product of those things, you just get the blocks. And so you can, if you want to try it by yourself, you can use this code snippet. I will briefly give you the solution. Okay, so this is exactly what I wrote here. We have for every row and for this is the rule that every value, every field has a value, yeah, and you want that no field has multiple values. This I forgot. Yeah, this needs to be added because otherwise it puts all the variables to true. Yeah. So this is essential. The next one here is what I wrote here. The next one is for the columns. This one is for the blocks. So I essentially use this is the Cartesian product for the blocks. You can have it. You can look at it more slowly afterwards. But this is the central idea is just the same like with the rows and columns. It's just a little bit more tricky to write because blocks have this weird shape. And in the end, you just start the solver, say Kadikar with this C and F, and you enumerate solutions, and you see that there's one solution, and by definition, it is a Sudoku. Because sometimes there are some Sudokus in the newspapers which have multiple solutions, because officially it's not a Sudoku then. Because a Sudoku is required to have exactly one solution, one completion. Okay. I also marked, this print function is a little bit long. I could have also just printed the value v by itself. I put this thing here with a star to indicate which was fixed and not. So just put this thing here if this looks too complicated for you. And the second part, end equals m is just a string, just makes Python not to start a new line after print if you're not familiar with Python. So you can see this also as a chance to learn to get in touch with Python in case you haven't. So I've been using Python really for years, and it's really a great language. So at least have a look at the examples if you didn't look at Python before. Okay, I think that's it with the examples for the first part. One specific question is now, here, if we fix all the values, there's no symmetries involved. But essentially, if we want to enumerate all combinatorial different Sudokus, if you want to say, I want to count how many Sudokus there are, do you really distinguish if you switch rows and columns and stuff like this? This can save your space a little bit. And if you think about symmetries, you might notice that every Sudoku can be, if you permute columns and rows, that you end up with a unique Sudoku at some point. And this is why do I mention symmetries here already? Because for Sudokus it might be boring to filter out symmetries, but for graphs this is what we usually do. If we want to investigate Ramsey numbers, we don't care which labels are at which vertices. We want to get rid of symmetries. And I will get to this in a moment now. So let's get back to the graphs, to the Ramsey. I have on the Colab, I have computed R33 equals 6, and you can see that this whole, I shifted a little bit, sorry for this. Okay, R33 equals 6, I computed here. We saw some solutions for 5, 5, 3, so we know that there are some graphs on 5 vertices, and for 6 there is no solution, which means that the R33 equals 6. To compute R34, if you look at 8 vertices, you will find a solution. It will say true. This only takes a few milliseconds. If you look for 9, you will notice it takes much longer. And this is not a coincidence, because in SAT, if you want to find a solution, and there's a rich pool of solutions because of all the symmetries, you will find faster a solution than to show that there is no solution. This is, even though the strategy of solvers are advanced and it's not brute force looking up, but unsatisfiability is more difficult in general. And if you go for R35, it only takes a few milliseconds to show that there's a graph on 13 vertices, but if you go for 14, this will take almost an hour. So you can run it on your local machine. Maybe it's a little bit faster then, but essentially this is force. This is force because I commented it out. So I ran it and wrote the comment that it takes almost an hour, and then I commented it out. So if you want to run all the sheet, I didn't want to burn your CPU energy, your battery. Just comment it in and you will see that it takes very long. And as I already spoiled, sorry, I shifted this symmetry thing a little bit above. No? Okay. So unset is difficult. So what we want to do is we want to break symmetries. This is very general. This is very helpful in general. For graphs, there's n factorially many solutions if the graph is asymmetric. If it has very high symmetry, then you don't save a lot by breaking the symmetries. But the average graph is not symmetric at all. And the question is, how do you get rid of isomorphic graphs? The first thing is you want to say, I break all the symmetries. I want to get rid of all symmetries. And then I just see the lexicographic smallest one. So I look at all the graphs. I bundle them into isomorphism classes, which are just like sets. And for every set, I just want to have, I just want to see the smallest one. And how do I do this? I will tell you in a second. But I can already spoiler you. This is very technical. So it's technical, and this means also the solver will have to do a lot of work. So sometimes this is not the best strategy to break all symmetries. Sometimes it's better to break the easy symmetries, and maybe this is already sufficient as well. And this is how I usually solve problems, to figure out like which are the symmetries to break. Because if you have like a factor n factorial and you save n factorial over 4. So there's a factor 4 which you could save still, but breaking this factor 4 requires a lot of energy to solve. It might take much longer. So you say, okay, I'm done. This is the trade-off, and finding this perfect spot. This is usually quite challenging, and and now how can you break the symmetries like the n factorial? Essentially for graphs, to make sure that the graph is the lexicographic smallest one, is if you have the edge list and you relabel the vertices, then you want that after relabeling it, it's not smaller. You can think of it like an edge list, or you can think of the adjacency list, adjacency matrix. Sorry. If you think of the adjacency matrix, what does relabeling of a graph do with the adjacency matrix? It permutes the columns and the rows simultaneously. So if you, for example, have a graph with some adjacency matrix, I don't know, whatever. Let's make it a little bit more interesting, maybe. I don't know. If you change vertex 1 and 2, what you do is you exchange row 1 and 2. Yeah, you exchange those two rows, and you exchange those two columns. Those are columns. Sorry, you exchange those two columns, and you exchange those two rows. And this is exactly what the permutation is. And this is rather tricky to implement. Yeah. So how do you do this in SAT? Essentially, you can think of writing your adjacency. You can think of your adjacency matrix as a string of bits. Yeah, you have like 0, 1, 0, 0. So this is like 1, 2, 3, 4, 5, 6, 7, 8, and you have some specific way how you go through this matrix, and you say for every permutation of the vertices, my initial graph should have the best string, the smallest one. And so what you have to do is for every permutation, so it means n factorial, you have n factorial many variables, more than times n factorial times n squared. So this will be not practical what I'm telling you, but there is an encoding. You can do this encoding for every permutation. You use this many variables to indicate the new adjacency matrix, and then you have to compare the two matrices. And how do you do the string comparison? This is another thing. Yeah. So if you have the two strings, you can introduce. You do it bit by bit. So you look at the first two, you say it's equal. Then you look at the next two, and you say it's still equal. And it can only be equal if it was equal before. And if you look at the next bit here, so there's a 1 Yeah, exactly. Here's a 1 and a 0, which means that the first one is bigger. It was equal so far, and in the next step, it's here. So starting at this moment, it will be smaller. And you have to encode this. You can do this with logic. It's not that hard because you do it step by step. So whenever you define one of those, you just look at the previous and you look at those. So it's always just considering three entries, and you say the next value depends on those. You add a lot of constraints, and you need auxiliary variables to do this, but it's possible. And this performs really not well. And if you want to do it better, you don't even need auxiliary variables. So the idea is to start with a SAT solver, to ask for a solution, and if it gives you a solution, I mean, what I'm telling you now is not their approach. Markus Kirchweger and Stefan Seider are located at TU Wien, so you might see them in this week. So what the strategy is, the general idea is to enumerate a graph, and then you have it in Python or C++, and then you go over all permutations. Maybe you don't even need to look at some permutations, because if you already noticed that swapping the first two vertices, why should you swap the last two? I mean, you can omit a lot of the permutations, and but in the worst case, you have to check a lot. And if it's not minimal, so if there's a permutation which made your adjacency matrix smaller, then what you do is you just tell the solver, no, this was not my solution. So you add another clause and you say, I want to get rid of this one. And you can do it more general. You can say, not only that this graph I don't want to see, and how do I tell the solver I don't want to see this graph? So the solver gives me a solution. It will tell me, so the solver gives me some variables. Yeah, it says x1 equals true, x2 equals false, x3 equals false. It gives me some list. How do I tell him to get rid of this solution? So I tell him the opposite. I say, add another constraint, and I want that x1 is false. So I say -1. I don't want, one of them should be opposite, or it should be +2 or +3. And by adding such a constraint, I make sure that this will never be returned again. So if I start again, I iteratively add clauses, I make sure to never see this again. And as I mentioned before, if swapping the first two columns already gives you a smaller thing, it doesn't matter what the adjacency matrix looks like here. So it could be that you can omit a lot of those things here as well. So there are some optimizations, how you can really prune the search space a lot. And this is nicely implemented here. And now there's a problem. Assume that you want to investigate Ramsey numbers. You know, or you expect that there will be an unset. Yeah? There's no solution. So this method never adds a constraint. So this symmetry breaking doesn't give you anything. So you just have worthless Python code which will never be executed. So what they are doing is they're building up a graph from question marks. Essentially, they start with question marks here, and they start filling it up and say 0, 1, 0, whatever. And at some point they notice, aha, now there's a conflict. And then they tell, this is not a valid, it's called partial graph. Yeah? So they use partial graphs to get rid of it. Or actually, there's different names for it. But dynamic symmetry breaking gets very complicated. You have to do a lot of engineering, but it really pays off. So this is the best currently performing technique for graphs. And it doesn't really need additional variables. It has few constraints. It's also output sensitive somehow, depending on the problem. Yeah. There's one central drawback. A SAT solver can only operate on the rules that you give him. If you tell him some constraints, it can only use those. It doesn't know what else you will give him in the future. So there's no way to look into the future. So unless you have a non-deterministic solver, but we are still not at this point. Yeah, that's it for symmetry breaking. You can definitely, if you're interested, look in this paper. And yeah, together with Stefan and Markus, I implemented some strategy, some dynamic encoding for planar graphs. Of course, you will say there's or not of course, but maybe some of you will already notice, okay, planarity testing for graphs is polynomial, which means there's a polynomial Turing machine. I have this Turing machine plus the algorithm. I can encode it with SAT. Yeah? So maybe some people already have this association. This is correct, but this is like a theoretical thing. Because if you think of a Turing machine and a graph planarity testing, good luck. I mean, if you have like 30 vertices or something, this will not really be practical. So in theory, there's a encoding, polynomial sized, but you don't want to do this. And there's another polynomial-sized encoding. There's several, I think, but the best one, which we implemented this one really performed okay-ish. It uses some description from Schneider, and it only uses cubically many variables, and we didn't get below this cubic factor. And surprisingly, using a dynamic encoding with the same strategy, like just give me a graph, I will look for an obstruction. So essentially, we used a boost library to check for a K33 minor or K5 minor. And whenever we find an obstruction, we added a constraint, say, no, this is not what we're looking for. Please continue. And
but you only added a constraint for that specific
for this.
K3 or K5.
Exactly. So we just say we use boost to find it. We see this K33, K5 in that solution. And maybe the K33 is spotted maybe only in this area. And as I mentioned earlier, then you don't care if there's a zero here or there. If the conflict is in this region, you can ignore what's outside. And this is implemented. And you can use this framework. SMS, so SAT modulo symmetries, is available. There's a nice tutorial online. We have a Python interface now, so it's really nicely accessible. But you have to make some C++ compilation. That's why it doesn't work on Google Colab. And as you see here, you can say, give me 6 vertices, minimum degree 3, at most 10 edges, list all graphs. This will immediately give you what you're looking for. This is from the command line. You can use it also inside of Python, where you say, give me a graph. I mean, you can essentially not just, you can, this makes the encoding. You say, I want to have graphs with 7. Maybe you can even go for directed. You can say planarity equals true if you want to have planar graphs. And then you add the constraints. This is like triangle free or something like this. Whatever. There are some examples. Yeah, this is triangle free. Yes. You just ensure that for every 3 vertices I, j, k, one of the edges is missing. This is the code for triangle free. And then you, with all graphs equals true, it will give you enumerate all solutions. You can also say I'm happy with one of the solutions. Depends what you're looking for. And now you might have spotted this equals 10. Yeah, I said I'm doing SAT solving. I have Boolean variables. I have Boolean constraints. How the hell do we do at most 10 edges? One approach would be again to use dynamic. Yeah, you could say as soon as the question marks are filled up, as soon as the number of ones is bigger than 10, you just cut. Would be a possibility. We implemented not this one, but we used it on the logic level. So what you do is you introduce auxiliary variables. I will briefly sketch it because I really think the idea is nice. I didn't put slides for this, so sorry for those who are watching. I hope you can see the slides. So the central idea is you consider one variable after another. You start with one variable and you make an indication to say this variable is true or false, which is essentially the variable itself. If you take the second variable, you make an indicator to say among those two variables, there's 1, 0, or 2 variables true. I didn't order it properly. Sorry, let me start over. Among 2 variables, there's 0, 1, or 2 true. And you do it iteratively. So whenever you go for the next variable, you don't have to look at all the variables. You just look at the previous counting indicator, you look at the next variable, and then decide. So it's just depending on 2 variables to decide the next. So actually I don't need to write it down, I guess. Also, everything is open source, and there's a PySat implementation. So just have a look maybe in the code here. Okay, I will maybe. It's also not that interesting to look at these cardinality encodings because there's what I would tell you now would be one of the less efficient ones, and there's multiple cardinality encodings. And if you look at this example here, you see it's quite optimized. So you can say I have 1,000 variables. I want to have 500 at most to be true. So the encoding which I would tell you would be worse now. But this one only suffices with this number times this number. So it only adds a few constraints and variables. And the trivial counting is if you say I have 8 variables or n, and I want to see at most n minus 1. Because what you do then is just to add the constraint that one of them is false. But this is the only trivial case. And as soon as you go further, you need more to cut. And if you don't use auxiliary variables, you can only do forbidding subsets. And if you have like n variables and you want to say at most n half of them are true, like this one here, you would have n choose n half, which is exponential cases to forbid. So it's really the thing that you should take in this talk is use auxiliary variables. And all the tricks are usually by modeling, by changing the model, by introducing stuff, or by optimizing in some way. But I hope you get the feeling. Okay, now we will. I already mentioned that you can solve instances just by checking the truth table. Here's the code. It's also on the Colab, and yeah, I mean checking the truth table. This is it's easy to say. Just take the CNF, check the truth table. You can do it by hand, but this is all the code that you need. Not entirely. You also need this one. But with this code, you have a SAT solver. So if you don't want to care about all these competitions of SAT solvers and how the optimized code looks, with these few lines, you can solve a CNF. And you can try and play around with this by yourself. It's online. I can briefly explain what's going on. If I have a CNF and there's no constraints, then I'm done. Yeah? Then the answer is true. If there's one clause which has no literals anymore, this is false. I will briefly get to those two cases, why this makes sense. Because what we do now is we recursively kick out variables and clauses. So those are the two cases. No constraints, we are happy. If one of the for every clause, we have to pick something. Every clause needs to be fulfilled, and if there's nothing left to fulfill, it cannot be fulfilled. That's why an empty clause is unset. Okay, and what's the strategy for brute force? just pick your favorite variable, and then look at setting it to true, setting it to false, and recurse on both parts. That's it. Here you have a perfect 2 to the n time algorithm for solving that. It's not really nice running time, but I have some benchmarks on the Colab. So here's the brute force strategy. This is the code, and I didn't explain the variables, but essentially it's just this code. For the literals, you just take the absolute value, yeah, because some of them might be plus or minus. You just take the absolute value, and the literals you get by just looking into all the so the CNF is a list of lists. So you just go through the lists, and there's also a nicer function, I guess, unflatten. So I could compress those 3 lines and just make it to 1 line, probably. But I didn't spend those 5 minutes. So you can reduce this code to 1 single line if you want. This code here. So I said, okay, this might be a black box still, but I want to remove this black box. If you have the CNF and you say, I have my variable, like, I don't know, 7. I want to set 7 to plus, and I want to set 7 to minus. What I do is I just go through every clause. If I set it to plus 7 and I see that one clause uses plus 7, I can just forget it. Yeah, this clause is fulfilled. We can just forget about this clause, and in this way we end up with no clauses. This is the nice part. So this is how we get to satisfiable. And otherwise, if the plus 7 is not in our clause, we can also kick out the minus 7, because minus 7 will never be possible. So every other clause which remains, which contains a minus 7, will remove the minus 7. And at some point, everything will be either removed, and we end up with an unsatisfiable one, or all clauses are satisfied. And you can try this brute force algorithm. It really works for Ramsey number 348. But if you start 349, you will see it takes really several minutes. It doesn't really perform well. And yes, now let's make a short exercise. If you're interested, the code which I have here just returns true or false. It just tells you, is it satisfiable or not. You don't have to write the code, but just think. But you can also do it. But we soon have the break anyhow. Just think, how would you adapt the code so that it returns a satisfiable assignment? Yeah? We not only want to see true or false, we want to see which assignment is the one. Yeah? Most people who are familiar with Python, they already know also how to enumerate. Maybe I leave this as a homework and use the last 15 minutes for something else. But you should definitely try to get in touch with Python generators. I think I didn't use any generator yet, but this is the perfect example. So in Python, it's super easy to enumerate all the possible solutions. So not only to return one assignment, but to return all of them. And you should just look at examples, Google for yield Python, and just start writing. And you will be surprised how nice this language is. Okay, let's go to the improvement, how brute force will be improved. And essentially, it's quite soon there is a game over, because as I said, there's no efficient algorithm. But this is an obvious improvement. So if you have a clause which only has one literal, it doesn't, like a 1 here, it doesn't make any sense to assume that -1. The only chance to continue is to put the 1 to true, to x1 equals true. So this is the unit propagation or unit clause rule. And as you can see, this SAT instance, if you just use the rule iteratively, it ends up with the empty clause, with no clauses, so it's satisfiable. And there's also another rule, which is called pure literal rule. You might notice that in this example here, there's only a +3. So it never makes sense to assume -3. So if you see pure literals, you can do this, and also in this example, everything resolves by itself, and you end up with without making any branches. And this is what SAT solvers try to do. They want to get rid of branches, because a branch gives you the exponential thing, and a unit propagation is linear time, if you implement it correctly. And the DPLL algorithm is precisely the old code, except that there's one additional line in the beginning where we say unit propagation. That's all. I mean, there's another variant if you look at Wikipedia, but I think the original was just unit propagation. But you can also do the pure literal rule. You can do both, but essentially already with the unit propagation, you have a significant change, and the performance of DPLL will be just a few seconds, where the brute force approach was significantly worse. Okay, and yeah, what does unit propagation do? The idea is quite clear. I provide all the code. You can have a look at it, how you would implement it. But essentially, I sketched it on this slide quite nicely what happens. You just check, is there one clause which only consists of one literal? And if, like here's the -2, here's the 3, this is exactly what you continue, and you replace the others. Like this clause contains a 1, so we are fine. The -1 will never be here. So the code below just does what's written here. It's not that interesting for now. You can still improve DPLL. So the current best algorithm is CDCL, and you might have noticed CADICAR previously. It's just they put letters CADA. CADICAR is just CDCL, and with heuristics, of course. And the idea is similar, like with the adjacency metrics that I mentioned before. They look for a conflict. So you have this recursive search tree, and if you find a contradiction, you don't just let me just draw it a little bit. You do this recursive search, and when you end up here with a conflict, you don't just go there. The idea is, at this point, you try to see, did I need all of those? So I had here 5 decisions, and it could be that already with those 2 you have a conflict. So this is what CDCL is trying to do. So it could be that that when you continue here, and you also look at, let's call this like x4 equals true and x5 equals true, and assume that there's a clause which says not x4 or not x5. It doesn't make sense to look at x1, x2, x3. You will always, if you look at this branch will always die. And CDCL, what it does, it will try to learn new stuff so that it doesn't have to look at those branches again. And by adding new clauses, it prevents of going into clauses, going into branches because of unit propagation. So at the point where it enters x4, if it already knows that this is not possible, it will not go into this branch. But maybe this was not originally a rule. It can learn at some point that this is not possible. I will give you an example from Wikipedia now, and then we go to the break. Or maybe it's even faster. I don't No, or do you? Yeah, let's just do the example, and maybe we can stop a few minutes earlier. I think it's a very nice time to stop. Okay, so this is a weird encoding. I don't know why Wikipedia has these hyphens. You cannot see the negation. Can you see the negations nicely? So this is the negation if there's this apostrophe. I don't know why they use it. Usually you have either the minus for the integers, or you have this bar on top, or you put the negate symbol, but for some reason they have it here. Anyhow, okay. They start branching. The first assumption that they do is x1 equals 0. The next assumption, okay, by x1 equals 0, the first clause tells you it has to be x4, because otherwise there's game over anyhow. So it learns x4 equals 1, and the next thing is it makes the assumption x3 equals 1, because there was no other, the only thing that you can learn if there's a unit clause. And if you assume x3 equals 1, those will be another unit clauses. And I think red means it's not satisfied and green is satisfied here. So what happens is you have to satisfy this not 8. So 8 is not satisfied. So x8 is 0. The same is for 12. So 12 has to be true. And sorry for the jumping. So I used the slide. I don't know why the Wikipedia example has so many jumps. I could have cut the images, but yeah. Yeah, okay. So at this point, you have to choose a branch again. x2 equals 0. Then you see, okay, 11 has to be something. And I think another branch, so x7 equals true. Now there's here, and at this point, yeah, okay, now we're done. Okay. Okay, so when you set x7 equals 1, you see that it has to be true and false simultaneously. So x9 has to be both, which is not possible. So it can analyze this tree in a smart way. You might have noticed that something appears here. So I didn't talk about what's happening here. Essentially, this is the implication graph. So when we set x1 equals to 0, it implied that x4 had to be set to true. And you have which of the settings implies what. And you see that the x2 didn't matter. So this whole decision here was completely, we could have directly went from x3 to x7. And this is what's detected in this tree. So what you do is just recognize the conflict and see what caused the conflict. It was just those three. So we don't care about x2. And the new clause that we learn is that this case must not happen. So we add a rule and say x3 must not be 1, or x7 must not be 1, or x8 must be true. Okay, and yeah, and then you just go back and repeat. Essentially, you can start over from top as well, but this is how they implement. So you don't have to do another x1 assumption. So essentially, if you use a deterministic rule, you would end up in the same branch again and end up with x3. But if you now repeat with this new rule, there will be another strategy. And at some point, you will completely get unsatisfiability, or you will find a solution. That's the idea of CDCL. And now this might seem like something completely different, but it's not. So there's a logic rule which says if you have A or B, and B can be a formula, A is a variable, and you have another rule which says not A or C, and C is a formula. I mean, both can be formulas, but what we need is A is a variable and B is a formula. Maybe I should have used capital letters. Sorry for that. So you can see those two like implications. Like the first one, it says not A implies B and A implies C. what is the conclusion if we have those two rules? In either case, B or C must hold. That's the logical consequence of those two things. And that's exactly what resolution describes. Resolution is just this implication. So if those two are fulfilled, then also this one is fulfilled. Now back to the example. If we look at our conflict here, it's not a coincidence that we ended up with this new rule, because we had here x, what rule is it? 5 and 6. So 1, 2, 3, 4, 5. This one here can be written like x9 or this thing. And this one is not x9 or that thing. So we just combine this one with this one, and that's the new clause. So instead of thinking of making this branching, you can think of CDCL also as this resolution strategy. And the nice thing about resolution is it can be checked like efficiently. Yeah? If you know what is the order of your resolution strategy, you can verify it. And this is how SAT solvers are certified.
Shouldn't the resolution say something about C instead of again saying A or B?
Yeah, the A is eliminated here. Ah, that's a typo. Sorry. Oh, thanks. Not so many typos, actually. I'm surprised. Almost made it to the end. At least none that I noticed. If you have some, please let me know. Okay, so we don't have to do this example. You can do this by hand if you wish. But if you use resolution, you will eliminate really nicely. Let us skip this. The last slide for this task session 1. Besides SAT, there's other concepts. You know, linear programming, whatever. It will be one of the next items. The obvious one is, if it's not satisfiable, you might ask, like, how many of the clauses are simultaneously satisfiable? This is called max-SAT. Yeah? There's a solver competition as well. So if you have a problem like this, there's people who deal with those issues. And essentially, what is done is they just use a SAT solver and cardinality encoding. So they say for every clause, they introduce an auxiliary variable. So if you have a clause which is like, I don't know, x7 or x8, what they do is they introduce a new variable calling y1, y2 for every clause, and they just try to maximize. Yeah, they want to see, is there a solution with at least this many? That's what's happening for max-SAT. Model counting, that's another thing. How many solutions are there? I have a SAT formula. I'm not happy just by knowing it's satisfiable. I want to know how many of the solutions exist. And essentially what is done is they try to split the instance into independent parts. It's a little bit difficult, but it works if you introduce auxiliary variables. So you introduce auxiliary variables, and then you have something like, I don't know, maybe you have a formula like x3 or x4, and then you have x1 or x2. How many solutions are there? Here are 3, because the truth table is if you just consider those two variables, there's 3 out of the 4. Here's 3 out of the 4. In total, there's 9 out of 16. So that's roughly the idea, and you can do some smart splitting. Instead of just going for Boolean variables, you can also use integer, reals, and data structures. And this is something that's really, there's strong development called SAT modular theory. I'm not going into details. As I said, there's so many topics where you can continue talks, lessons. The basic idea is to use indicator variables. For example, if you use integers or real variables, you just use indicator and they say, this is bigger, or this is a nice link. You can click on it, and you will, or just remember set free. It's 2 letters, set and free. Just Google it. There's a lot of literature about it. All of you know linear programming. You can, instead of just using this existential question, you can also use multiple quantifiers. There's people trying to solve it, but QBF is difficult. B-space complete, of course. Yeah, not so much luck. Usually, if you end up with a problem from QBF, it's always difficult to solve. But for two quantifiers, there's this group in Potsdam. They develop Klingo. It's a solver for what they called answer set programming. I'm sure there's also other solvers than Klingo. But if you have two quantifiers, this is a nice language. It looks like, for me, it looks like Prolog. It's not exactly like Prolog. If you have seen Prolog in some of your courses in your studies, it's interesting to look at. But don't expect, if you have multiple quantifiers, that it's solvable. Because already with one thing, it's NP complete and often not possible. Yeah, that's the next thing. Thank you. I promised you some applications. So far, we only had small exercises. I'm going to tell you about problems that you can address. So on one hand, you can prove or disprove existence of some structure. Yeah, that's the obvious thing. You model something, you want to know, is it possible to do this graph or not? As mentioned earlier, satisfiability is easier than proving that nothing exists. Yeah? Because usually in the search space, if there's a solution, this is not general, but a rule of thumb, if there's a solution, usually there are more solutions. And it's Hello. Oh, it works. So far. Okay, thanks. I don't hear this, yeah? please keep me updated. Okay, induction basis, if you want to do some induction and you have, you know how to prove the step, and then there might be the case, we had this for one paper, where you really needed, it was 11 points or something. So the statement was clear how to continue with more than 11, but you needed at least this many points to make it work. And if you want to prove a statement of 11 points in the plane by hand, this is really difficult. Actually, we did this specific thing, which I currently have in mind, not with SAT solvers, but it would be possible to do it with SAT solvers. But just keep it in your mind that you can sometimes save a lot of time by doing things by computer. And even sometimes it's possible to do inductive steps. So if you can reduce the inductive step to a finite problem, if you can you do something from left to right, it could be infinite. And if you could argue on some
Hello. Okay. Beatboxing. It's always weird to hold those things. Okay. Induction base, induction step, and so on. The three applications that I'm going to talk now are L-shaped point-set embeddings. Thorsten will also be at GD. I think the others not. Yeah. And the last one is really a big topic, so maybe I will skip through the second one to really do the third one, because this is kind of really a nice result.
Just give me one which works for
Okay, so what? Yeah, that's cool. I think we can keep it this way. Yeah. Okay, so the problem is as following. Ignore the text. Here's some pictures. You're given a point set, and you don't have points on the same x and y coordinates, and you have a tree, or in general, you can formulate it for graphs. But this was the question that motivated me for my master's. Yeah, and the question is, if I have this point set and this tree or graph, can I draw the edges like with one band along the grid so that the whole thing is planar? That was the question, and there was some results on the minimum number of points, on the maximum number of points that you need, so that for every point set you can draw this tree inside, and you don't use all the points. But it was unclear whether n points work. Yeah, so there were some upper bounds, like okay, if you have n squared points, then essentially, let me draw a picture, because it's kind of related to Ramsey theory, and you will hear about Scheucher. So at some point, if you start drawing enough points, you will find a large subset which is either increasing or decreasing. I don't know, like this one. So either you find something that's increasing or decreasing, and you can prove it. And essentially, the n squared was really kind of cheating, because what they said is, if you have n squared points, there's a theorem also by Erdős and Scheucher which says you have n increasing or decreasing. So essentially, they were just looking at the very trivial case that the points are just like in this way, and they said every tree can be drawn like this. You do it from left to right, greedily, whatever. Yeah, okay. So that was essentially the theory. Not that kind of interesting, but what really interested me was the question: can I do something non-trivial from the bottom? Yeah, and I managed to prove something from the top as well. But the bottom took me. This was 2016-15 was my master thesis, and it took me really until I think it was 2019 or something, 18. It took me several years to find one example to show that it's to find the example, a tree and a point set. And yeah, so what did I do? Okay, how do you model such a problem in a SAT instance? So the only thing that you can model, I mean, essentially the question from a logic point of view is there a point set and is there a tree such that there exists no embedding, yeah? Whatever this means. So this is like for every embedding, it is non-planar. So essentially, what is this? There might be another quant or whatever, but you see that it's not a SAT instance. And to make things with SAT solvers, I had to fix the tree and the point set. So for a fixed point set and for a fixed tree, I made a SAT instance and tried to figure out whether it works or not. And the variables that I used is, for the mapping, I say vertex I is mapped to point Bj, and I say for every pair AB, I think for points or edges, I don't remember. You can look it up. But essentially for A and B, I introduce. I think it was for points, but never mind. For A and B, I decide is the edge going up or downwards, if there is an edge, and so on. Yeah. Now maybe I guess it was on the graph, because otherwise it doesn't make. Okay, A and B were vertices. So it's kind of misleading because I drew it on the they already located at points, but it's in an abstract sense. So wherever A and B are placed as vertices, the variable indicates that the connection to the vertex A is horizontal. So you don't know where the vertex B is placed. Yeah? You have a vertex A, and somewhere there's this cloud, and somewhere there's a B, and the connection here is horizontal. It could also be on this side. Yeah, you don't know if A or B is to the left. That was the encoding, the variables, and for the encoding, we were interested in n points into n vertices. So it was a bijection actually, but you can go injective as well. It's the same. Yeah, I'm not going into details here. You already know how to do this, but you see it's essentially what I showed you in the first part. It's quite simple, and by just putting all those things together, yeah, I have these variables for the mapping. Yeah, this is just for the mapping to say that this is an injective mapping. And how do I make sure that the edges have these patterns? This is a graph theory question, or you can consider it like this, because now if you have what is this? This is what's okay because of this. Yeah. Okay. I at some point I learned not to use it. It's kind of weird. So what I was doing here, I used my old slides. Yeah. This was maybe now I would tell myself from the past, don't do this. Yeah. I essentially have two variables for the same thing, and this one is just a negation of that one. Yeah. So you can just save a lot of code by just writing AB instead of. I mean, this is an XOR essentially what you see here. So one of them has to be true and one of them has to be false. Yeah, not so smart. You can do it, but it doesn't really give you a lot. And also subsolvers figure this out by this propagation thing. So as soon as you set one of them, it will directly give you the other value. So subsolvers are really smart. So it doesn't matter even if I would change the old code, it would not perform better or worse. It's the same because of these propagation properties. But from a readability point of view, yeah, it's not so nice to read this code. And no. Okay, so there's certain patterns you don't want to see. I don't want to have edges like this. Whenever I have a vertex, it can only have vertex to degree 4. That was the specification. Of course, you could say this is still a planar graph because they are just in an epsilon environment. But this was the specification. And how do I encode something like this? Assume that you have 3 points, P, Q, R, sorted from left to right. And now you have vertices A, B, C. Or actually VA, VB, VC. I used V to indicate if it's a vertex or otherwise it's a point. So if A maps to B and B is mapped to Q and C is mapped to R, and then you also have the edges. So there's also the edge PR and PQ. So then I don't want that both of them are horizontally connected. And to write this as a clause is exactly here. So it's not allowed that A maps to B, B maps to Q, C maps to R. Maybe you should go on the other side. Sorry, it's always disappearing if I step in front. Sorry, that was didactically not smart. So I don't want that those 3 points are where the vertices are mapped to. I don't want that the connections are both here. And I only add this constraint, of course, if A, B, C have the edges. Yeah? If there's an edge from A, if there's an edge from A to B and an edge A to C. So I have a very large code and I say if AB is an edge and AC is an edge, and I do a lot of constraints for every triple of points, for every triple of vertices, and here I don't use combinations but permutations. This can definitely be optimized, the code, but I hope you get the idea how this was done. And you can exactly the same way forbid those patterns. The results, in the beginning it was frustrating because we, for up to 12, we didn't find something. And it looks like, okay, it's just 12, who cares about such small numbers? There's so many, there's 12 factorial many point sets, and I spent 100 CPU days, more than 100 CPU days into proving this. Because for every point configuration and every tree, you have to test this. And I used to do this on, I still do those commutations on clusters, and 100 CPU days is really a lot of wasted energy. But at some point I found this. Yeah, let's switch. Okay. Now maybe this way is better. Is it back? Yes.
No, it's just a thing for putting the microphone there. They don't have replacement.
Okay.
I'm holding it.
Yes, that looks super comfortable.
They unfortunately don't have a replacement. The other thing is batteries.
Game of Thrones style or something like this. Okay. Shame. Okay. Okay. So we have this tree and this point set, and they didn't map. You cannot see this immediately, I guess. Or does anyone see why it works? It's not that intuitive, and also checking it was not that straightforward. We have a handwritten proof at some point, but even if you see the picture, it's not 100. You don't immediately see why it's true, and this shows how difficult it was to generalize it, and we didn't manage to generalize it to an infinite family. We found examples for up to 20, but what we did is for slightly modified. It's a weaker statement, a weaker theorem. We said that if the cyclic order of the tree is prescribed, and in the original problem this was not fixed, but if the cyclic order was fixed, then this particular pattern here, which we also had here, then this particular pattern does not work. And this was, even this statement, it covered several pages to prove. And but it was a cool result. And we learned a lot also how to use SAT solvers. This I think I did with C++ and also Minisat instead of Kadicar, even though Kadicar was better in the performance because the instances were so small. And Kadicar does a lot of heuristics, and Minisat was just straightforward. So sometimes try to check out also other options, slower options, because they might in some situations perform better. You will actually see this. If you start Kadicar in the first milliseconds, it will just do some weird hashings and stuff, which makes sense in general, but I didn't want to have it here, and this saved really a lot. Okay, the next project is also on point sets and graphs. This is what I usually work on. The question is, give me a point set. No, the question is there a point set which is n-universal? And n-universal means that every graph with n vertices, actually there's a more general notion which is called, if you have a graph family, so you have a family and a fixed parameter, like n is the number of vertices. So you have like all graphs with n vertices which are planar or something like some constraints. And you want that for all of those graphs you can find a straight line drawing on this point set. That's what is called universal. Yeah. And we wanted to we just restricted to planar graphs. That's why we called it n-universal. But in general, there's this notion universality for a specific thing. There's a lot of literature. The best bounds currently are you can do planar graphs on a grid. It's not n by n grid. You just take a small part of the n by n grid, and essentially. I'm not going into this. But there's a nice theory around this. But as you see, the upper bounds are quadratic, the lower bound was linear. What we did, and some people tried to figure out what about small numbers. And there was a computer investigation. So there's up to 10 points. There's a complete database in Graz with Osman Eichholzer where you have all combinatorial differently point sets, and for up to 10 points it was verified that there was one of them, finding it, I mean there's a million point sets, but if you have it, you just remember it, checking it is much easier than finding it. And there's also proof that 15 does not work. Our contribution was to show that 11 does not work, so the gap here was not entirely closed, because we know that there's no 11 point set for, it doesn't mean that there's for 12, 13. So this is not it doesn't really give you an induction. Yeah? They proved the induction. It's not an induction, but they proved that for every n, by some counting arguments, for every n larger than 15, there's more graphs than you could ever embed, and this was essentially the idea. And we managed to also improve some constants here. But I'm just talking about this result, because if you want some exercise, yeah, maybe let's think about it. Okay. Yeah, now maybe it's time for a small exercise. Okay. The question is: you give me a point set and a graph. How would you check using subsolvers whether it has an embedding? Just one graph. How would you do this? I already also provide a hint here. Yeah, if you have coordinates like x and y coordinates, you can look at the determinants of those matrices. They indicate whether the points lie to the left or to the right. And if you want to know if two edges cross, this is what you have to avoid for planarity. You can just read those signs, because if you have a point C to the left and D to the right of the line AB, and the same thing happens here. So if you look at the segment DC and this separates A from B, then it's a crossing, and otherwise not. We don't allow collinear points. So there's no point on a common line, no 3 points on a common line. So does everyone have an idea how it would work, or should I go into detail a little bit more? I don't have to go into detail, but okay, then I just continue here. So essentially, if you have one instance where you check whether one graph can be embedded on the point set, you can essentially do all graphs simultaneously. You just concatenate all graph instances. You just make an and you will see. You have to make sure that the variables are disjoint. You cannot use the same variables, but you will have one very big instance, and it's satisfiable if every graph is embeddable on this particular point set. And now the cool thing is there are some constraints. So if you make variables also for the orientations here, not every assignment for those triple orientations. So essentially there's like cubically many triple orientations, and only this gives you like 2 to the, no, let me write it down, it's too much. So this space is something like a cubic in the exponent, but essentially only 2 to the n log n are actual point sets. So it's really only a little. And there's something in between. There's like something that's called pseudo point sets, the pseudo order types, abstract order types. They have a quadratic exponent. And this one can be nicely characterized. I will talk about it more close in the next part, because here it didn't work out anyhow. But just as an idea, it's possible to formulate it, but there was no chance to make it work. So what I did was essentially just going over all order types, checking the instances. And the nice thing is, if you want to find universal point sets, I mean, spoiler, I already said there's none for 11. You just need to find for every point set one graph that doesn't work. Yeah, that's the idea. So as soon as it's game over, you can forget it. So at some point we found out that there's no universal point set. There's this many graphs, this many point sets, planar graphs. And you don't need to check all planar graphs, you just need to check triangulations, yeah? Maximal planar graphs. And what I did, as I said, essentially for every point set, I just want to find one specific graph. So I made kind of a priority queue whenever a graph kills a point set, I put it to the front. Yeah, this was roughly the strategy. And at some point, when we knew there's no universal point set, we also tried to make some we tried to find the smallest configuration of graphs that does not work simultaneously. Because here, like 1,000, we knew there's no universal set, which means those do not simultaneously embed. But if I just take one graph, it embeds. Yeah, and because for every graph, I make a drawing and then I look at the coordinates, that's my point set. And the question is how many do not work? And we figured out 49 was possible. And the previously best thing was 7,000. Yeah? So already by proving that for 11 there's no universal point set, we improved this 7,000 to 1,000, and we managed to get down to 49 by really some clever trick. I didn't put it here. You have to read the paper if you're interested. Now, but the idea was we fixed like 25 where we thought like this is a good potential set, and then we looked for which point sets are not yet covered, and by fixing 25 graphs here, or maybe it was 20, I don't remember how many, we fixed some graphs, and by fixing those graphs, this number really decreased. It was just 100,000s. And then we had like the remaining graphs, minus 25, and we only had like 100,000 point sets. And then we just made a matrix and filled in zeros and ones and tried to see which is the minimum cover. So we tried to select as few so that every point set is killed. Yeah? And this was done, we did with integer programming. Okay, and now to the last topic for today, the empty hexagon theory. And the work was with Marijn Heule, who is like one of the head researchers or leading researchers in SAT solving. And it was really a project that I was working on for I think more than 10 years. I mean, I started with my bachelor on this particular problem, not on the empty hexagons, but in this direction, and I learned about it in 2013, and we managed to solve it in 2014, so 10 years was, I had it in my mind quite some time, and at some point it worked, so it was really nice. And before I tell you about the empty hexagon problem, let me go one step back. So the thing is, based on the Erdős-Szekeres theorem, what is this? As before, we don't have 3 points on a common line. So we have general position. If you have a point set, we say a subset is a k-gon if those points lie on the convex hull, on the boundary of the convex hull. So no point lies inside. So this is a 5-gon. Actually, it's an empty 5-gon, or also called 5-hole. We will use this later. And this is a 6-gon, but it's not a hole because there's something inside. But for the Erdős-Szekeres, for the classical problem, we don't care if there's something inside. That's the important thing. Yeah. So in the beginning, the question was just about the gons. Yeah. The containment didn't play a role. And yeah, we have this theorem by Erdős and Szekeres, which they proved already 100 years ago almost, that if you have sufficiently many points, it's a Ramsey-type argument. If you have enough vertices, you will find either a large clique or anti-clique, and Erdős and Szekeres proved if you have enough points, you will find a subset. And this is actually the only avoidable configuration. So Ramsey says either this or that, and in the point sets, you only have this structure. It's stronger in some sense, because you know which pattern you will see. And the first numbers were easy. Esther Klein found out that if you have 5 points, you will find a 4-gon. So the fourth Erdős-Szekeres number was just 5. So it's the minimum number of points to guarantee a k-gon. So the Erdős-Szekeres, they said if you have enough points, then every set of this many points will give you a k-gon. So the question was, how big are those numbers? That's the question, yeah, that we look at. And G of 4 is 5, because if you have 5 points in the plane, you will have either 5 points on the convex hull or 4 points on the convex hull. In both cases, you are done. And if you have 2 points in the interior and only a triangle on the hull, you will see a foregone here. And interestingly, here you can even take this foregone and it's empty. So just for later, I will not go into this for later. The next step, G5 equals 9. So 9 points give you a 5 gone. You also have to show, also for the previous one, you take a triangle with 1 point in the interior, then you know that you need at least 5 points. Because those are, if you take a triangle with 1 point in the interior, it's not yet a foregone. So you need at least 5 and at most 5. So that's why it's equality. And if you determine the next value, G of 5, here's 8 points with no 5 gone, and they proved by case distinction that it's not. Every 9 points give you a 5 gone, and it took quite some years. This is 70s, and this was only 20 years ago when they determined the next value. So Erdős and Szekres actually conjectured that those are always. If I go back one slide, this was 5. 5. Here is 9, 17. So the conjecture was always power of 2 plus 1. And they provided a construction. So the lower bound was constructed quite some, I think in the 60s or 70s. And here they proved that 17 points always give you 6 gone. As you can see, this was a quite time-consuming calculation, but also the hardware was of course slower. I managed to verify it with SAT solvers in only 1 hour. And to be fair, if you check out the speed up of computers, this was something like 50 CPU hours with nowadays hardware. So it was a factor of 50 in the. So it was still some improvement, a big, and now we managed to get it down to 10 seconds. So it was really the same. Essentially, it's the same, but we did a lot of tricks to make the empty hexagon work, and this was just a side result. So I'm just showing you the shadow of what we did, and the shadow looks already nice, yeah. And as I said, Erdős and Szekres conjectured this exponential lower bound with powers of 2 plus 1. The upper bound was of magnitude 4 to the k for many years, and in 2016, Andrew Suk, they also have a Bach also has a paper here, but I think it's presented by Gesa Todt, so he will not be here most likely. It's not so important who is here or not. I just want to say it could be that Janusz Bach is at GD, but Gesa is presenting nothing. They showed. Instead of 4 to the k, it's 2 to the k plus error term. And you see, it's only this small thing, but this small thing is really difficult. So a lot of people, as you see, 1 year later, they slightly improved the error term here, and it's still open. And as I mentioned already, today we talk about empty guns, which are called holes. Yeah? It's not a 6-hole because there's something inside. And similar to G of k for k gons, we look at H of k for k holes. And we want to figure out, so Erdős asked, is it true that that this number is finite? Is there always, for every k, is there a k hole in every sufficiently large point set? And in the beginning you have the same thing. Yeah, I mentioned already, if you have 5 points, there's a 4-hole. And Harbord showed, okay, before it was G of 5 was 9. Harbord showed, okay, you need 1 more point. 10 gives you a 5-hole. So it's not the same. It's not the same question. But could it be that it exists? And the answer is no. So Horton immediately showed, not immediately, but only a few years later showed there's large point sets with no 7-hole. And as I said, the triangle with 1 point is not that interesting. Here we see again the 5 points, which do not give you a 4-hole. No, sorry, this is the proof. Sorry, just ignore what I said. The central thing is that this looks nice still. Yeah, you see here, you can verify as a human that this is 9 points with no 5-hole, yeah, and actually it's collinear. So you could say these 3 points are aligned because you think of a small epsilon, but this is just for means of. I don't know why I made this wrong. But I wouldn't have to tell you. It could be also 1 pixel off. Okay, but actually, if you look it up, you will see that it's collinear in the PDF. Maybe I fix it. Just one pixel, and then I'm happy. Okay, so this is all doable by hand up to this point. And if you look for 6 holes, the best set was 29 points. And this one does not contain 6 holes. And at this point, you can, as a human, can you say that there's no 6 hole? I have no idea. Yeah, you can only use computers at this point. So it was quite clear already in these years, in the early 2000s, that computers are necessary to really get into this direction. And actually, this is the truth. Yeah, so this is the best counterexample. So they show this guy Overmars showed that 29 points is not possible. So the next value would be 30, and he said he could not find any larger, and actually 30 is the answer. And that's what I'm going to tell you how we managed to do this. But before some other background still, the Horton set. So the large sets with no 7 holes, they are constructed essentially like hypercubes. You just start with 2, you make a copy high above, slightly shifted to the right, and you recurse on this. And there is some argument. If you just go on and on, the argument is if you assume that there's a 7 hole, yeah, assume that there's a 7 hole somewhere hidden, then there's 4 points. It's distributed over some layers. Yeah? If it's only in the upper part, then we just look at the previous thing, and here it will be on both. So there will be some recursive layer where it's both on top and at the bottom. Yeah? So the 7 hole has some points on the top and some points on the bottom. So 7 is equal to 4 plus 3, or 6 plus 1, or 5 plus 2. So those are the options. And actually, if you have more than 3 points on one side, like here, they have to face up. And as soon as you have 3 points here, there will be something in the middle by construction. And that was the central idea of Horton's construction. And this is almost foolproof. Maybe I forgot something now. But yeah, what about 6 holes? What I already told you, we solved it. Otherwise, I wouldn't tell you. But this was open for a long time. And in 2008, Gerken, he announced it in 2006. So he was first. Niklas, 2007, published faster. It took DCG 1 year longer to publish it. But essentially, Gerken wrote 35 pages, and also he got the Richard Rado Prize of Mathematics, which was really because it was a nice result. And he proved that every 9 gone. So if you have a 9 gone, then you will find a 6 hole. So this implies that G of 9 is bigger than H of 6, and this means that this is finite. Yeah? And the best bound is something like 1717. Yeah? And this is a 35-page case distinction. And some years ago, I verified his proof, because it was a very long case distinction, using SAT. So I essentially modeled all the things, and instead of making case distinctions, I just put the statements of the lemma. And a SAT solver said, like, don't do this. I cover this for you. Yeah? I noticed also that the 29 construction by Overmars can be found really very fast. But if you start the instance with 30, it ran for months. So my conjecture at this point was that this really is the truth. And we showed that 30 is the truth. And as I mentioned earlier, the key ingredients for the proof is the variables A, B, C gets plus if it's above, or D is below, so it's a minus. What do I mean by above and below? This is for directed lines, and you can write it with determinants. And in this whole slides from now on, I will also assume that the points, if the labels increase, like A is smaller, B is smaller, C, then they are sorted from left to right. So above, below is really a relation. So it will never happen that A is to the left of B, so that above, below is an issue. But often this makes troubles. Okay. So we have variables A, B, C, orientations of A, B, C to indicate how the relative positions are, and here's the ETR complete. Yeah. So in the talk in the morning, it was announced that I will speak about ETR. So this is my ETR talk. I will now continue with the rest. It's somewhere between P space and NP. Yeah. No one knows where it exactly lies. No one knows it could be equal. NP could be P space. P could be P space as well. Who knows? Very unlikely, but it's not. No one proved this. So it's a difficult problem to realize. If you have an assignment to make a realization, it's difficult, which implies there is no axiom system. You cannot even axiomize it, because if you could write an axiom system, you would have a subsolver to classify it, and then ETR would be the same like NP. So if there would be encoding, we would prove with this encoding equality here. So the best thing we can do is pseudo configurations of points, and this is this thing here. Yeah. So instead of point sets, we go here, and this is like the no constraints. We have the cube. We only have a quadratic thing, but it's still there. As you see, most of them are not realizable. But what constraints are those? If I look at 3 points in the plane A, B, C, the point C lies either above or below, and if it lies above, I mean it's mirrored. I will just put this case here. The other one is completely the same, just flipped upside down. If I look at 3 points, you can look at those rays, and the next point, if I have index A, B, C, D increasing, the next point can lie either in this region, this region, or this region. And if you look at the triple orientations A, B, C, this is plus, yeah, we already know. The D, if it goes down, it will always change just one sign. And surprisingly, if you write down ABC, ABD, ACD, BCD in this lexicographic order, you have a staircase. So those are the points. If the point D goes from here to here, you see this nice shape here. You can also see this differently. If you look at the variables in lexicographic order, the number of sign changes from left to right is at most 1. And as I said, C could be below, so you have the same staircase also. This is not really interesting. But those are the constraints. And this is the characterization of abstract order types. And this is, maybe I should make a star. Yeah. So if the points are sorted from left to right. Let me not talk about order types, but this is what we do here. Yeah, we want to have this n squared thing, and we look at exactly point configurations where we have exactly this property. This is the only requirement that we put, and actually this characterizes pseudo configurations in this setting. And how can we ensure this? Yeah, quite easy. We just look at every 4 tuple. We have n points. N is 30. Yeah, we have 30 points, and for every subset of 4 points, we require that one of those patterns happens. How do we require it? 4 variables have 2 to the 4, so there's 16 options. I have 8 here, which means I just have to forbid the other 8 patterns. So I just write down for every 4 points, I forbid the other patterns. I don't want to see them, and by forbidding the other 8 patterns, it implies that if the subsolver gives me a solution, it will be one of those because the other 8 are forbidden. Okay, I forbid those. There's, as I mentioned, oriented matrix, order types, whatever you call them, rank 3 signotops is this is the accurate name for this combinatorial structure. You can continue reading on this, but it's not in the focus for today. Okay, we have now a characterization for pseudo configuration of points, and now we want to make this Erdos-Zekaras problem. We want to encode it. We need an indication variable to say, is a point x inside or outside of a triangle? And again, essentially, we just look at all those 8 cases. Yeah, here, if the point is here, no point is inside. If it's here, the point C lies inside of the triangle. If it's here, nothing is inside, and if it's here, it's the point B which is inside of the triangle ACD. And I really introduce variables to indicate this. And those are the cases of containment. So I really write down those cases. It's a little bit of work to do, but essentially this is everything. And based on these containment variables, I know that this formula looks really terrible, and it's not really something. If you show me this formula, I wouldn't recognize it by myself. Yeah, I mean I match it to this because it's here. But if you wake me up middle in the night and say, "Look, Manfred, this is the formula," I was like, "What do you want?" I mean, you don't see it from the logic, but it is. Yeah, I can tell you. And now, if you accept this. You have to accept this. Sorry. So you can continue reading if you don't trust me on that. But now it gets easy. If I have 3 points A, B, C, and they should form a whole, what does it mean? It does mean that there's no point X which lies inside. That's the characterization of a empty triangle. Yeah. So I can just say I have a new variable which is the same like the logic end of all those negated incontainments. And how does a 6-hole look? A 6-hole is just a set of 6 points where, this is forbidding 6 holes. Yeah, I don't want to see 6 holes. So I say for every 6 points, I don't want to have a hole, so it means one triangle must contain a point. So I say for 6 points, I add like OR on all the triples, which is essentially 6 choose R constraints, literals in each clause. So I have n choose 6, so it's not, it's n choose 6 subsets, which could be 6 holes, and each of them has this many literals. And this is quite terrible actually, but it works. Yeah, so this is the first encoding. You can run it. And to make this encoding a little bit better, we try to reduce those factors. And spoiler, we will get down to n to 4. And this was one of the key things for making this work. And how do we get down? I mean, without auxiliary variables, it's game over almost, except for this small trick here. So if you consider this subcase here, yeah, you have ABD 0, this is this thing here, this is 0, BDF 0, so it means that those 4 points look like here, and the same thing from below. So you have 4 like this, 4 like that, and the interesting thing is, as soon as you have this pattern, you know that there's a 6-hole. It doesn't mean that those 6 points form a 6-hole, but it means that there is somewhere a 6-hole. Sorry, I was missing also this. Okay, sorry, that's not true. Yeah, it's good that you look skeptic. No one was nodding, so okay, I missed the central part. If ADE is empty, if there's no point inside of this region, then I know that there's a 6-hole. Now you start nodding, now you get the idea. Because this might not be empty, so there could be points in here or in here, but you don't care. Just take the closest one, that's it. And this is the first improvement. So we use this improvement, and you can encode it now like this. Yeah? And you continue like I mean, this was only one case, yeah? So this was only the case where you have 4 points above and 4 points below, but essentially there's 16 such cases, which are all analogously. I'm not going to go through 16 cases now, this would be boring, but essentially all of them look like this. They have orientation variables and one h variable. Before, remember that all of those 20 were all negated h variables, and now the O's really play a central role. Yeah? And so you have like the O variables, you have the H variables, and then you have like what is a 6-hole. And before it was like very focused here, and now the 6 holes really operate on the on the O's. So it was really somehow a positive outcome, which we also observed. Yeah, we didn't know this in the beginning that this has a such big effect, but it really played a role. And now another thing, how we get down to n to the 4, as I already spoiled. In this case, if you have 4 points above and 4 points below, you can introduce a new variable, and you say A, maybe A, capital A is bad because we use also A, B, C as a lowercase. But okay, we have a capital A to indicate that there's a foregone above the line AD, like BCD. But it could also be some other point in between here or something else. And it should also say containing also C. So it means that this point, and this point here, they form a foregone with some point, and this other point has to lie somewhere here. So we use one variable for this, and as you look in this formula here, this essentially was just the encoding of there's a foregone above and a foregone below. And this is what we did here. We use above and we use below. And now the formula was not 4 times O and H, it was just A, B, and H. And with these additional variables, we don't care about the B here and this point here. Here it's labeled B prime, before it was labeled differently, I think. But with this, you only have n to the 4 clauses, because those constraints here can be formalized with n to the 4. So you have a nice encoding of size n to the 4. And it's there's even a more general encoding. So you can, there's a n to the, actually there's a cubic time algorithm for detecting k-gons. But we can only do n to the 4 with a SAT encoding because of the Boolean variables. You can have a closer look, then you will see why. So essentially, the issue is if you have a RAM model, yeah, you have registers, you put integer variables. I need indicators, yeah, and for the indicators I get this additional blow up of n. So that's why I lose this linear factor. But still, for any k, there's a dynamic program for testing k-gon existence or k-hole existence. K is fixed, because if k is n, then it would scale up again. But yeah, so this can be done for any k-gon, k-hole. We only need 6. This is the last implementation exercise I'm going to skip. So I put the code of the Erdős-Szekeres encoding. If you want to have a look, it's there, and I just put a very simple encoding there. So the actual code is much more complicated. I showed you some of the optimizations. There were many optimizations. It's still not super complicated, but I tried to keep things as simple as possible. But you can have a look here, if you wish. And now let's compare the encoding. So this was the original one, the very straightforward encoding for the 6 holes. Then we made this improvement with the H variables. So instead of having like 20, I just have 1. So you see the runtime on this benchmark instance really dropped. And then we introduced n to the 4. So it significantly dropped. And then there were some additional removal of redundant clauses. It was like 15% or something like this. But this was just a benchmark instance. As I said, the whole thing was like on a cluster with 2 CPU years. So we always had to work on some smaller things and make extrapolations. But there's some statistical evidence, of course. Yeah, as I said, this was like 40 CPU hours. In nowadays hardware, we managed to get it down to 10 CPU seconds on the 6 GON problem. And if you say, if you have a SAT instance that runs for 2 years, I wouldn't stand here and tell you about it. So what we did is parallelization. So you can essentially, if you have a SAT instance, you can split it into 2 SAT instances. One you say x1 equals 2, and the other one you say x1 equals 4. Solve them simultaneously, and I can promise you, if you do this, one of them will take 99% of the computation time, the other one 1%. So it's tricky to find a good splitting strategy, and this is really one of the core tasks in SAT solving. And we were benchmarking which one is the best splitting strategy. I'm not going much into detail here, just to see that we tried several splitting strategies. This one performed quite well on our specific instance that we wanted to solve. My co-author made some colorful pictures. It looks really nice, but it doesn't say so much. And here you see, this is interesting actually. This shows you the running. This is not just colorful. It shows you the running time logarithmic scale for the actual cubes. So we said like, okay, we have to split our instance into this many instances. They are called cubes because hypercube, you can think of the solution space of 2. You have n variables, so it's a hypercube, very big, and you just think of it like subcubes. That's why people call it cubes. We have this many cubes. The running time was about 2 CPU years, and you see it was nicely distributed. I mean, there were some increases here, but only like a factor of 10 above the or maybe 20 or something. And usually, as I said, if you do some splitting, you will end up with a curve that goes through the ceiling. Yeah, I mean, not on an exponential scale, but on an exponential scale, it can still go up very, very steep. And yeah, all our model was verified. I mean, we verified the SAT solver result, so we used these DRED certificates. Actually, there's a newer technology. It's LRAS, but you see the D becomes an L. Anyhow, so the thing was verified, and also the encoding. So not only that the solver worked correctly, we also have a formal verification where we really start with algebra. We say like, okay, real values are describing the coordinates, and we say this is our SAT encoding, and it says, okay, points really have those coordinates. And you might know, okay, that doesn't help. Okay, let me skip down a little bit. I will tell you. It's the last slide anyhow. At this point, you trusted me. I told you those are the only variables. This is a proof by picture. I mean, it's a solid proof by picture because it's correct, yeah. But at this point, you could have said like, I don't believe you. But I said those are the only 8 possibilities. And with Lean, you can verify this rigorously. So there is no human error. It could be that that there is some hidden cell somewhere or something that we overlooked. I mean, obviously there cannot be much more. But if you have more than 4 points, you can make mistakes in pictures, yeah. And then you miss some cases. And if you use Lean, you will get you can formally prove that everything is correct. And that's what they did. So we answered the long-standing open problem. SAT seems to be really very good technology, many open problems, blah, 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 not only for Erdős-Szekres. Those are Erdős-Szekres slides. That's the end of my talk. Thank you very much.